All right. Well, Chapter 9 is all about alcohols, ethers, and epoxides. There is a small section in here about thiols and sulfides and disulfides. However, we're going to be primarily looking at the alcohols, ethers, and epoxides, these oxygen-containing compounds. So first, we're going to start with a few definitions. And our first definition that we want to look at is what is an alcohol? In order for our compounds to be classified as an alcohol, they need to have a hydroxy group, but that hydroxy group needs to be bonded to an sp3 hybridized carbon. So it needs to be bonded to an alkyl group. All right. So that means a tetrahedral carbon. It's not going to work if it is a trigonal planar carbon, sp2 or sp. Needs to be an sp3 hybridized carbon. We can classify alcohols. By how many carbons the carbon with the OH group has attached, just like what we've done with other things. So, for example, this is a secondary alcohol because there are 2 carbons attached to the carbon with the OH. And then this one is a tertiary alcohol because there are 1, 2, 3 carbons attached to the carbon with the OH. And then finally, this one is primary. So we want to be able to classify those. And we have a problem like that here in just a moment. All right. For hydroxy groups that are on sp2 hybridized carbons, they fit into a different category and are going to be discussed at later points. So compounds having the hydroxy group on the sp2 hybridized carbon, a trigonal planar carbon, those are either going to be enols or phenols. And they have different kinds of reactions and different kinds of chemistries that we will look at. So an enol is where the OH is directly bonded to the carbon that is part of a double bond, and a phenol is where we have an OH that is on an aryl. We're going to talk about enols in Chapter 11. That's coming up relatively soon. And we'll discuss phenols in Chapter 19. That is in the second semester. All right. And now we want to look at ethers. So ethers have 2 alkyl groups bonded to an oxygen atom. And so here are a couple of, this is a generic ether. This one is a symmetrical ether. We call it a symmetrical if it has identical alkyl groups on either side. And we call it an unsymmetrical ether if there are different groups on each side. We can have aryl ethers included in the broader category of ethers. It won't undergo some of the reactions that we will talk about later in this chapter, but it does have a lot of similar properties. So we typically will include this in the category of ether, although we'll end up calling it an aryl ether just to specify. So we're going to look at number 39. Okay, so here is number 39. And the question is, or the problem is, draw the structure of all 7 compounds with the molecular formula C4H10O. So there's going to be some that are alcohols and some that are ethers. We may have seen this previously in a different problem set, but let's just go through them. So one thing you can do is to be systematic about it. So if you draw a butane, so there's butane, and then we add an OH to that, that will be one of our compounds. That one is butanol. All right, and so if we do the same thing but move it to the second carbon, move the OH to the second carbon, then that will be another alcohol. All right, there is another one. That's tert-butanol. And then there is isobutanol, which is that one. So it does ask us to label each of the alcohols as primary, secondary, or tertiary. We'll go ahead and do that. And then we'll draw the ethers. There's only 3 of those ethers. So this carbon is only attached to 1 other carbon. So this one is primary. This carbon is attached to 2 carbons. So this one is secondary. This carbon is attached to 3 different carbons. So that one is tertiary. And then this carbon is attached to 1 carbon. So this one is primary. So we have 1 of each of those examples. For the ethers, we have the symmetrical ether, which is diethyl ether. We'll talk about naming these here in just a bit. So that's 1 of our choices. And then another one is this, where we have a methyl and a propyl group. And then we have 1 additional one where we have methyl and an isopropyl group. And we want to label these as either being symmetrical or unsymmetrical. Well, clearly this one is symmetrical. So that is a symmetrical ether. This one is going to be unsymmetrical because these are different. So that is unsymmetrical. And of course, this one is also going to be unsymmetrical. All right, so there we go. That is our 7 compounds. Those are the only possibilities. If you think you can think of another one, you should ask me about that in office hours or send me an email. Those are the only 7 I can come up with. Our third category of compounds in this chapter is epoxides. And epoxides, they're a special category of ether because they have an oxygen that is in a 3-membered ring. So oxygen in a 3-membered ring. Epoxides are called oxiranes. That is sort of their official nomenclature. So you can call this an epoxide or you can call it an oxirane. When you see things that are epoxy resins, they can contain epoxides, and they use some of the chemistry that we talk about in this chapter. They use some of that to cross-link and get a very hard resin structure when you're using epoxides. So epoxides are kind of cool things to use. All right. The carbon-oxygen-carbon bond angle here is at 60 degrees. And if you look at this oxygen, you will see that it is sp3 hybridized. And the typical sp3 hybridized angle is going to be about 109.5. So epoxides with that angle of 60 degrees, that means that they are under quite a bit of angle strain. So there's quite a bit of angle strain in that ring. That means that these are going to be much more reactive than you would expect from just a typical ether. So we can do all kinds of interesting chemistries on these epoxide rings that we can't do on a regular ether molecule. So we'll get into that as we go through this chapter. All right, so when it comes to the structure and the bonding, the oxygen atom in the alcohols, the ethers, and the epoxides are always going to be sp3 hybridized. So typically, we're going to see bond angles around those oxygens close to 109.5. Here, it's a little bit less on this alcohol. On this dimethyl ether, it's a little bit more. And then, of course, the exception is with the epoxides. The epoxides are going to have that strained angle of 60 degrees. So alcohols and ethers, yes, though they'll have typical angles close to the 109.5. Because the oxygen atom is a lot more electronegative than carbon or hydrogen, we'll find that these carbon-oxygen bonds and the oxygen-hydrogen bonds are quite polar. And with the OH bonds, they are capable of hydrogen bonding. So we get a lot of interesting interactions that will occur with these dipole-dipole interactions, and with the alcohols, hydrogen bonding interactions. If we look at the electron density on the oxygen atom, look at it on an electrostatic potential map, we'll see the red represents a partial negative charge. So here on the alcohol, we'll see a partial negative charge on that oxygen, partial positive charge on the hydrogen. For the ether, we still get that partial negative charge on the oxygen, but the partial positive charges are going to be on the carbons, which means they're going to be a little bit more spread out than they are with the hydrogen on alcohols. With epoxides, we'll see that that oxygen sticks out a little bit more. That's part of what makes it more reactive, of course, in addition to the angle strain. So epoxides, there's all kinds of things that will make it more reactive. But the oxygen ends up being electron rich. So the oxygen ends up being electron rich. All right, so now we want to look at nomenclature. And doing nomenclature for alcohols is pretty straightforward. We're going to build on what we've learned so far. The first step is that we want to find the parent chain with the OH group and change the ending to all. All right, so here we've got 1, 2, 3, 4, 5, 6 carbons in that longest chain. And so 6 carbons would be hexane, but we're going to change the ending to all. So this is hexanol. Now, something interesting that we do when we number it, we want to number it to give the OH the lowest possible number. So in this case, we're going to number this one from the right. So 1, 2, 3. 1, 2, 3, 4, 5, 6. All right. When you're naming it, you want to place the number immediately before the hyphen all. So we're going to break up the word hexanol, and right after the end, we're going to put the location. So hyphen, the number, and then hyphen, and then all. It looks a little strange, but that is just how we like to do it. So we'll call that hexane 3-all. So hexane 3-all is going to be that. Now we just need to add the substituent on there. There is a methyl at the 5 position. So this is simply going to be 5-methyl hexane 3-all. So 5-methyl hexane 3-all. When we're doing cyclic alcohols, like this one with the OH on a cyclohexane ring, we'll just change the parent chain, which is the ring, change its ending from ane to an all. So we'll change the E to an all. And so this is a cyclohexanol. Now we haven't named the substituent yet. We'll have to name that. We want to number the ring starting with OH as carbon 1. All right, and then the ring is going to be numbered either clockwise or counterclockwise so as to give the next substituent the lowest possible number. In this case, we want to number it counterclockwise, so this will be 1, 2, 3, and that will give our methyl the number 3. And because the functional group is at carbon 1, we usually omit the 1 for the cyclohexanol. So we don't need to call it cyclohexane 1-all. We can just call this 3-methyl cyclohexanol. All right, to practice that on another one, here we've got this one. So as far as numbering this, we want to make the OH the number 1, and then to number this to give the next substituent the lowest possible number, we're going to number this one 2. All right, so 1, 2, 3, 4, 5, 6. And then, so this is a cyclohexanol. We've got 3 methyls, 1 at the 2, and then 2 at the 5. So this should be 2,5,5, 2,5,5 trimethyl cyclohexanol. And there I see an error. I'm going to fix that. And through the miracle of pausing the recording and editing it, It is 2,5,5 trimethylcyclohexanol. So 2,5,5 trimethylcyclohexanol. There are common names for alcohols, and sometimes those will be extremely useful, and sometimes they won't be as useful. The common names are for the simpler alcohols are alcohols where we can name an alkyl group with a particular common name. So you name all of the carbons in the molecule as a single alkyl group, and then just add the word alcohol to it. And so a couple of examples of this would be like methyl alcohol. Now, typically we would call this methanol, but this methyl alcohol is one word, one name that we can give this. It's a common name. This one would be ethyl alcohol. This would be propyl alcohol. Here's isopropyl alcohol. That's the active ingredient in rubbing alcohol. This is tert-butyl alcohol. And then this one is isobutyl alcohol. And we actually saw tert-butyl and isobutyl alcohol. We saw that on number 39, the one we just did a few minutes ago. And then here is benzyl alcohol. This is a benzyl group. So a benzene ring with a CH2 that makes a benzyl group. Okay. So now we want to look at diols and triols. This is where we have 2 or 3, and we can extend this to 4 OHs would be a tetraol, 5 OHs would be a pentaol. All right, so diols, triols. To name a compound with 2 OHs, you just add the suffix diol at the end, and then you put the numbers of where those diols are immediately before. If you've got a triol, you will put triol at the end. And then you just want the parent name of the alkane. We're not going to drop the E in this case. We're just going to call it the alkane diol, the alkane triol. And then numbers are used to indicate the locations of the OH groups. So here are a couple of examples. The common name for this is ethylene glycol, but we can call this ethane 1,2-diol. So ethane 1,2-diol. This is glycerol, that's its common name, but we can call this one propane 1,2,3-triol. And then here we've got the cyclopentane 1,2-diol, and we can specify that this one is trans because the OHs are opposite each other. All right. Some smaller compounds often will have common names like the ethylene glycol and the glycerol. And there are quite a few of these kinds of compounds. So let's go and look at the in-class assignment. And we're going to give the IUPAC name for each of these alcohols. All right, so let's count here. We've got 1, 2, 3, 4, 5 carbons in that chain, and then there's another methyl that's attached. So 1, 2, 3, 4, 5, and then OH. And then so 1, 2, 3, 4 on the 4th carbon, we're going to have another CH3. We're going to number this. So here's carbon 1, 2, 3, 4, and 5. And so we've got a methyl at the 4 position, and then this is pentanol, but we're going to call it pentan 1-ol. So the name for this would be 5, or not 5, it is 4. I meant to say 4. So 4 methyl pentan 1-ol. All right, now I'm going to let you guys in on a little secret. For most of my life, I would have called this 4 methyl 1 pentanol. But it turns out in the 90s they switched the official IUPAC nomenclature. so that instead of putting the one before the pentanol, you put the one right in front of the ol. So this flows a little better, but this is the official name. So that is our official name. All right, on this one, I definitely recommend drawing out a skeletal structure and figuring out what is actually in the skeleton and what is not. So we've got CH3-2. That means both of these CH3s are attached to that one. So one's on the end, and then there's that one. CH2, CH. The CH2CH3, that is an ethyl group that is attached to this carbon. And then a CH with an OH attached to this carbon, and then CH2CH3 is on the end. So we're going to count out the number of carbons that are in the main chain. So 1, 2, 3, 4, 5, 6, 7. So we'll count those out. I'm going to draw it again. So 1, 2, 3, 4, 5, 6, 7. And then, so on this carbon, we've got a methyl. So we'll put a methyl there. And then CH2, CH, and on that carbon, we have an ethyl. And then on this carbon, we have an OH, and then CH2, CH3. All right, as far as numbering, we want to give the OH the lowest possible number. It might seem like, oh, we want to give our first substituent the lowest possible number, but that is not the case. We want to give our OH the lowest possible number. So we'll do 1, 2, 3, 4, 5, 6, 7. All right, so what that means is that we have a heptan 3-ol, and then our substituents are going to include a 6-methyl and a 4-ethyl. All right, when we put that all together, this the heptan 3-ol is going to go at the end. The methyl and ethyl are going to go out front. We want to do them alphabetically. So ethyl comes before methyl. So this will simply be 4-ethyl 6-methyl heptan 3-ol. Okay, so that one, not too bad. All right, now let's look at this one. We want to find the longest chain, and preferably that has the OH on it. So 1, 2, 3, 4, 5, 6, 7, 8. If we just do these, that's 7. So it's definitely going to be with the OH in it. So 1, 2, 3, 4, 5, 6, 7, 8. All right, and I numbered it to give the OH the lowest number, so that would be octan 3-ol. So octanol, and the OH is at the 3 position. And then we've got a 5-methyl and a 4-ethyl. All right, we'll want to put those in alphabetically. Ethyl comes before methyl. So we'll do 4-ethyl, 5-methyl, octan 3-ol. And that is the correct name. Okay. On this one, we've got a diol, and so if we count this off, 1, 2, 3, 4, 5, 6, it is a 1,4-diol. The parent chain is cyclohexane. So cyclohexane. So it's going to be cyclohexane 1,4-diol. And then one other thing is that we have stereochemistry here. There are no stereogenic centers because this is achiral compound. There's a plane of symmetry that goes right through those OHs. So there's no there's no stereogenic centers, but we do have cis-trans chemistry, and in this case, it is cis. So we will put a cis out front, and then cyclohexane 1,4 diol. So cis cyclohexane 1,4 diol. All right. Next, here we've got just one OH. So this is an alcohol. We have cyclohexanol. All right. And the number, we'll do 1, 2, 3. That will give our methyls the lowest possible position as the 3 there. We don't need to put a 1 in front of the all because it's implied that the OH is at position 1. But we will need to put the 3 in front of the dimethyl that is there. So when we put that all together, we'll have 3, 3 hyphen dimethyl cyclohexanol. All right, and finally here we've got this one. So 1, 2, 3, 4. We've got a 2, 3 diol. The parent chain here is 4 carbons, so that's butane. So it's going to be butane 2, 3 diol. And then we will need to specify the stereochemistry. So if we look at carbon 2, we've got hydrogen in the back, and that's convenient. Oxygen is the biggest atom, carbon 3, and then carbon 1. That's clockwise, so that's going to be 2R. And then for position 3, oxygen, carbon 2, and carbon 4, that's also clockwise, so it will be 3R. So we will get 2R, 3R, butane, 2, 3 diol. All right, and that is the nomenclature for the alcohols. So let's go back. And now let's look at, we'll look at the nomenclature for ethers and epoxides. We'll start with the ethers. There's 2 ways that you can name ethers. You can name them with common names, and if you've got like a symmetrical ether, or if you have 2 alkyl groups and they're simple alkyl groups that you can name, then you'll simply put the 2 alkyl groups with a space in between, put them alphabetically, and then put the word ether afterwards. If there are 2, if it's a symmetrical ether, then you'll just put a di in front of the name of the alkyl groups. So this one would be diethyl ether as an example. All right. And then pay attention to stuff like butyl comes before methyl, and sec. We don't include the sec as part of the alphabetizing purposes. All right. The other possibility for ethers is to name them using the IUPAC method. And for that, you will find the parent chain, which is the longest chain, longest hydrocarbon chain, and then name any of the the simpler alkyl group as an alkoxy group. So if you've got a methyl, it would be methoxy. Ethyl would be ethoxy. So you can do that. So for example, that's a methoxy group. This is an ethoxy group. This is a tert-butoxy group. This is particularly useful when you've got a more complicated structure, something where you can't really name the 2 with simple alkyl names. So you'll just name the parent chain as an alkane or whatever it is, and then you'll name these as alkoxy groups. All right, so name the parent as that. There are a few specialty ethers, some cyclic ethers like tetrahydrofuran, and we'll talk about a few other ones a little bit later. But this one is a commonly used solvent for organic chemical reactions. All right. When we're doing epoxide nomenclature, well, we run into some interesting things. And the reason we run into these interesting things is that there are three different ways of naming epoxides. So, three different ways of naming epoxides. One is a lot more dated, and then the other two both fall into the range, into the category of being IUPAC. So, it gets a little bit tricky here. So, epoxides, you can call them epoxy alkanes. That's one way to do it. You can call them oxiranes, or you can call them alkene oxides. And the first two, the epoxy alkanes and the oxiranes, those are both IUPAC nomenclature. And then the alkene oxide, that is a common nomenclature, and we'll talk about it here in just a moment. So to name as an epoxy alkane, first you name the alkane chain or the ring or whatever your parent chain is to which the oxygen atom is attached, and use the prefix epoxy. And then you will use two numbers to designate the two carbons, the two adjacent carbons that oxygen is attached to. So for example, this one is 1,2-epoxy cyclohexane. This is 1,2-epoxy methyl propane. So carbon 1, carbon 2, and then there is the epoxy that is in between those. And here this one would be 2,3-epoxy pentane. And you'll notice that there is a cis-trans stereochemistry. So this would be cis. If we had a dash line here, it would be trans. So all kinds of interesting things can happen when we're doing that, when we're looking at that. To name something as an oxirane, well, for an oxirane, you would name the ring as an oxirane. So this is oxirane. So that's going to be your parent chain, and then you name anything that is attached to it. Because when we're doing oxiranes, the oxygen counts as position 1, then your substituents are always going to be at position 2 or at 2 and 3. In this case, they are at position 2. So you can't have substituents on the position 1, because position 1 is an oxygen and it's already got all the bonds that it's going to have. So the oxirane ring always has the oxygen atom at position 1. And then you just name, and there's no need to number. There's no need to number for a monosubstituted oxirane. So if you just have methyl oxirane, it has to be at position 2. All right. And then finally, naming epoxides as alkene oxides. And this has to do with how most of the epoxides are made. Usually we take an alkene and we oxidize that alkene to form an epoxide. So, for example, we can take ethylene and convert it into ethylene oxide pretty easily. And manufacturers will do this by the ton. They will make lots and lots of ethylene oxide. So there is ethylene oxide. There's also things like propylene oxide and so on. So just mentally replace the oxygen with a double bond, name that alkene, and then just throw the word oxide after a space. All right. This is a common name way of doing it, and I will show you some examples of how we do that when we look here at number 41. So go back over to our document camera. All right, so we have to figure out what kind of compound it is first. Well, this is just a regular ether. And so we want to name this as an ether. We can do a common name. So our common name, and then we can also do an IUPAC name. Now, most people would call this by the common name, because we have two cyclohexyl groups, and so we would call this dicyclohexyl space ether. So dicyclohexyl ether. For the IUPAC name, we would name one of these as the chain. So we would have a cyclohexane, and we would have a cyclohexoxy group attached to it. So that we would call cyclohexoxy cyclohexane. And there is no space in between those two components. So the cyclohexoxy would be this part, and the cyclohexane would be this. So it's a cyclohexoxy on a cyclohexane. Most commonly, you're going to see the dicyclohexyl ether as the name for this. All right, this next one, we're only going to do the IUPAC nomenclature for this. And that's because, that is simply because here is our ether. And while this is a propyl group, this thing is, doesn't have a simple name. So we don't have a really simple name to put on there. And if we tried to make it a really simple name, it would end up being really, really ugly. So let's name our longest chain and give our substituents the lowest possible number. So we're going to number from the right side here. 1, 2, 3, 4, 5, 6, 7. So we have a heptane. All right. And then the things that are attached to it are a 3 propoxy. So this is a propoxy group. So propyl changes to propoxy. So a 3 propoxy, and then we have 2 methyls at the 4 position. So 4,4 hyphen dimethyl. All right. And then we need to decide what's going to go first. Well, M comes before P alphabetically. So we're going to do the 4,4 dimethyl first. So 4,4 dimethyl 3 propoxy heptane. And that is the name of that compound. As I mentioned, there's not really a common name for it because the 4,4 dimethyl heptane, there's not a quick and easy name for that. So, all right. On this one, we can have both a common name and an IUPAC name. So we'll do both of those. So the common and the IUPAC. So for the common, we need to identify the two components. We've got an isobutyl, and here we have an ethyl. So what comes first alphabetically, isobutyl or ethyl? Well, E comes before I. Remember, with iso, we use the I as for alphabetizing purposes. So we are going to have a ethyl space isobutyl space ether. And like I said, that is the common name. For the other name, we're going to name our longest chain here. We'll call this 1, 2, 3. So that's a propane. And then on there, on propane, we've got a 2-methyl and a 1-ethyl. And when we're trying to decide which one goes first, E comes before M. So we'll put that ethyl first. 1-ethyl, 2-methyl, 1. It's not 1-ethyl, it's 1-ethoxy. All right, I'm going to fix this. So that's going to be 1 ethoxy 2-methyl propane. So there's an ethoxy on the propane and a methyl on the propane. And that is our IUPAC name. So I nearly messed that one up. So ethyl isobutyl ether would be the common name, and our IUPAC name 1-ethoxy 2-methyl propane. All right. So here, as I mentioned previously, we've got 3 different ways for naming epoxides. So I'm going to do the epoxy method first. So 1, 2, 3, 4, 5, 6. So we've got a hexane and a 1,2 epoxy and a 2-methyl. So when we're naming that, let's see, E comes before M, so we'll have 1, 2 epoxy, 2 methyl hexane. All right, so let's look at how we would name it if it were an oxirane. And I'm going to redraw it. 1, 2, 3, 4, 5, 6. I'm going to redraw it because we number things differently when it's an oxirane. So we've got 1, 2, 3. On position 2, we've got a butyl and a methyl. Butyl is going to come before the methyl. So we will have 2 butyl, 2 methyl oxirane. All right, and that is another way of naming it. All right, there's one other way of naming this, and that would be if we thought of this as being an alkene that got oxidized, and that alkene would look like this. So 1, 2, 3, 4, 5, 6. So if we name that alkene is 2-methyl hex 1-ene. So 2-methyl hex hyphen 1-ene oxide. And so that would be another way of naming it. Probably the easiest way is to name it as an epoxy group. And that's the way I'm going to recommend most of the time. Naming it as an oxirane will also work many of the times, but it won't work in cases like this where we have a cyclic structure that also connects to that epoxide. All right, so let's go ahead and number this. So 1, 2, 3, 4, 5. So we have a cyclopentane. So cyclopentane. And then on that cyclopentane, we've got a 1, 2 epoxy. And we have a 1 ethyl. And we have to decide which one of those is going to come first. Well, the epoxy will come first. So we'll call that 1, 2 epoxy 1 ethyl cyclopentane. All right, so 1, 2 epoxy 1 ethyl cyclopentane. Sorry, it got a little messy there. All right, and as I mentioned, you can't really name this as an oxirane because we've got this bonded here. It gets really difficult if you try to do it that way. We could name it as an alkene that got oxidized. So this is 1-ethyl cyclohexene. So 1-ethyl cyclohexene oxide. All right, and then here on this one, we've got an ether, and there are two ways to name this. We can do the common name, and we can do an IUPAC name. And the IUPAC name almost seems absurd on this one. So the common name is di-tert-butyl space ether. So di-tert-butyl ether. And then the IUPAC name, we're going to name one of these as a tert-butoxy group, and then the other one we're going to name as a propane. So 1, 2, 3, and it has a methyl on it. So it's going to be a propane, and we've got a 2-methyl and a 2-tert-butyl or butoxy. So a 2-methyl and a 2-tert-butoxy. Tert doesn't get included for alphabetizing purposes. So we're going to put B comes before M. So this will be 2-tert-butoxy 2-methyl propane. So 2-tert-butoxy 2-methyl propane. Okay, let's go back and look at this. We're going to do physical properties, and then after physical properties, we will stop the video. So for the physical properties, the number one thing that will dictate the physical properties is that we've got a whole bunch of polar bonds that are here. The carbon-oxygen and the carbon-hydrogen bonds are all polar, and so we get extensive dipole-dipole interactions. With the oxygen-hydrogen bonds, the alcohols are capable of intermolecular hydrogen bonding, and therefore they're going to have stronger intermolecular forces. We can say they're more polar, but really they just have stronger intermolecular forces because the hydrogen bonding is our special case of dipole-dipole. All right, so we'll find that alcohols tend to have stronger interactions than the ethers and the epoxides. And then there's also an interesting steric effect that occurs with the hydrogen bonding. More highly substituted alcohols are more sterically hindered, and that increased steric hindrance decreases the ability of the OH to do hydrogen bonding. So we'll find that we'll increase the steric hindrance when we have a more substituted alcohol. So tertiary alcohols have more steric hindrance than the secondary, which is more than the primary. And where this has an effect is on the boiling point. So if you have molecules that are the same size, but one is a tertiary alcohol and one is a primary alcohol, that primary alcohol will have a higher boiling point because it's less sterically hindered. And so we'll see that when we look at the physical properties here. All right, so what we talked about a minute ago, so alkanes, they don't have any dipoles in them, so they have fairly low boiling points. Ethers have at least dipoles in them, so they're going to have higher boiling points than your regular alkanes. And then the alcohols will have even higher boiling points because of the hydrogen bonding. Here is that steric hindrance. We've got tert-butanol, sec-butanol, and then just 1-butanol. And you'll find, or N-butanol if you want to call it that. And you'll see that the tert-butanol with more steric hindrance has the lowest boiling point. The sec-butanol with a little bit less steric hindrance has a higher boiling point. And the 1-butanol with the least steric hindrance has the highest boiling point. When it comes to solubility, we will find that the solubility of most of these compounds with the oxygen in them are going to be in water. If it's less than 5 carbons, we will get some solubility, at least enough to make it so that there's a decent amount dissolved in the water. You may still get some phase separation, but you'll get quite a bit that will dissolve in the water. Once you get more than 5 carbons, they're going to become water insoluble. And then we'll find that pretty much all of them will be soluble in most of your organic solvents. All right, so let's look at number 44 on the in-class assignment. And we want to rank these in order of increasing boiling point. So here we've got an alcohol, another alcohol, and an ether. The ether should have the lowest boiling point. So we'll put that ether first. So that's that one. That'll have the lowest boiling point. Now we've got propanol and isopropanol, and the more sterically hindered will have a lower boiling point than the less sterically hindered. So we will do the isopropanol next, which is this one, and then our highest boiling point is just going to be the regular propanol. So lowest boiling point in the middle and the highest boiling point. For water solubility, on this one, we just need to look at the number of polar groups here. So here we've got hexanol, here we've got hexane diol, and here we've just got hexane. Well, clearly the least soluble in water is going to be that hexane. So 1, 2, 3, 4, 5, 6. That's going to be the least water soluble. For these, this one has 1 OH and this one has 2. Well, the more OHs it has on there, the more soluble it's going to end up being. So we'll find 1, 2, 3, 4, 5, 6 OH. That one will be a little bit more soluble than the hexane, or actually quite a bit more soluble, but the one that will be a lot more soluble, 1, 2, 3, 4, 6 OH. All right, I got cut off there, OH. All right, that one will be the most soluble because we have more hydrogen bonding capability interacting with the water. All right, we're going to cut that video off and we'll start the next part. On the next part, we're going to be looking at some interesting alcohols and interesting ethers and some interesting epoxides.